Our second lesson in Module 2 is Lesson 2.2, looking at scientific notation with positive powers of 10. Our goal for this lesson is to convert big numbers to scientific notation, and then also to take scientific notation and convert those back into big numbers. Now, the definition of scientific notation might not make very much sense to start with, but as we get into it, I think you'll understand it a little bit more clearly. But our formal definition is this: it is a method of expressing very large and very small numbers as a product of a single-digit number times a power of 10. So essentially what that means is we're going to take a single-digit number. Now there might be a decimal behind that single-digit number, and that's fine. But we're going to take a single-digit number and then multiply that by 10 to some power. And that's what the trick to this lesson is going to be, identifying what the exponent behind the base 10 needs to be. So let's go ahead and get into it by taking a look at our first example. Example 1 says a blue whale weighs 250,000 pounds. We want to write this number in scientific notation. So as we said before, scientific notation needs a single-digit number and then multiply that by 10 to some power. So what we're going to do is we're going to take that number 250,000 and rewrite it. And we have to ask ourselves, all right, right now in this number, where is our decimal place? 250,000, there is no decimal that's written, but the decimal is actually behind the last zero. But we need to ask, where do we want that decimal place to be? As I said earlier, we want a single-digit number. So that means we need to move our decimal place to where we have a single digit in front of the decimal. So a single number to the left of the decimal. So what that means is we want to move our decimal over to right here. Okay? Now, in order to do that, I like to make what I call ocean waves underneath each place value. Okay, so what I'm going to do, scroll back down. So what I'm going to do is I'm going to make what I again call ocean waves underneath each place value until I'm able to move my decimal to where I want it to go. Okay? So the thing we need to realize is that we made 5 ocean waves here. So that'll give us 2.5. Okay? I move my decimal place all the way over so that it's in between the 2 and the 5. Now we don't have to include all those zeros behind the 5 because they're really just place value holders. We do need the 5 because it's a specific number, but the zeros, those are just place value holders, so we don't really need those. So we've got our single digit number, 2.5. We have a single digit to the left of our decimal place. That's what we're looking for. We want a number between 1 and 10, just under 10. And so it's 2.5, and it says that we multiply that or times that by 10 to some power. Okay? And so what we need to do in order to identify what our exponent is going to be, we go back and we count up those ocean waves. Because there's 5 ocean waves, our exponent is going to be 5. So we get an answer of 2.5 times 10 to the 5th power. That's an equivalent number to 250,000. They're both of the same value, they're just written different ways. Now here are the key things that we need to identify when we're looking for a number in scientific notation. Again, we need a single-digit number in front of the decimal. So if we have 2 numbers to the left of the decimal or a 0 to the left of the decimal, that does not count. We need a number between 1 and 9 to the front of our decimal. Okay? So we need a single-digit number there. We need to multiply. Okay, we need to multiply. And we need to have a base 10. So those are the things that we're looking for. So here, 2.5 times 10 to the 5th power. And since it's a word problem, we want to use the correct label. So 2.5 times 10 to the 5th pounds. Okay? Let's take a look at another one. For our second example, it says the distance from Earth to the Sun is about 93 million miles. We want to write this number in scientific notation. So we're going to go ahead, rewrite the number. Okay, so we have our number 93 million miles. And what we're going to do is we're going to identify where the place value is, or where the decimal place is, and also where the decimal place is supposed to be when we're writing in scientific notation. Right now, our decimal place is behind the last 0, but we want it to go between the 9 and the 3 because we want just that single digit number in front of the decimal. So one more time, I'm going to make ocean waves until I get my decimal over to in between the 9 and the 3. So since I moved the decimal over, I now have 9.3. I don't need to include the zeros because they're just place value holders. I have a single digit number to the left of my decimal. Now I remember that I have to multiply by 10 to some power. We need to identify what our exponent would be. So we go back, we count the number of ocean waves that we had to make in order to move our decimal from behind the last 0 to in between the 9 and the 3. So when we count those up, we end up with 7 ocean waves. So we end up with 9.3 times 10 to the 7th power, and we include our label, which is miles. Alright, so those were 2 examples where we took a number written in standard form, a big number written in standard form, and we rewrote it in scientific notation. Now we have to do the opposite of that as well. We need to take a number written in scientific notation and we need to convert it back into standard form. So let's go ahead and take a look at a couple of those. Third example just says write 3.51 times 10 to the 7th in standard notation. Okay? Now because this number here, we look at this exponent for a lot of information. First of all, we want to identify if it's positive or negative. Okay, we'll get to negatives tomorrow or maybe the day after, but what we're looking for is we're looking for it to be a positive number, and if it's positive, that tells us that our standard notation is going to be a very big number. Okay, positive exponent means a very big number. I want you to write that down. A positive exponent means we're going to have a very big number. Write that down. Now, in order to convert this number 3.51 times 10 to the 7th power, we're going to write that first part down, 3.51. And now we ask ourselves, all right, if this number is supposed to be a very large number, and we're going to make our ocean waves again, which way do we want to make our ocean waves go? If it's supposed to be a very big number, do we want our decimal to go to the left, or do we want our decimal to go to the right? Think about this. Which way would we move our decimal in order to make this number a large number? In order to make this a very large number, what we want to do is we want to move our decimal place over to the right. So I'm going to make 7 ocean waves going over to the right. There's my first 2 going underneath the 5 and the 1. And now even though I don't have any more numbers, I'm still going to continue and make 5 more ocean waves. Okay, so I have a total of 7 ocean waves now. I have an ocean wave under the 5, another one that's supposed to be underneath the 1, and then 5 more ocean waves that are just empty. So what am I going to do with those empty ocean waves? I'm going to fill those in with zeros. Alright, so now I've moved my decimal from behind the 3, from in between the 3 and the 5. I moved it to behind that last 0. And so now I've got my number written in standard form. I'm just going to go ahead, copy it down, including all the zeros. Now I go back, and I make sure to include my commas. So 3.51 times 10 to the 7th power in standard notation is going to give me 35,100,000. And since it's not a word problem, there's no labels to give this problem. Alright, for our 4th example, this one is a word problem. It says the mass of one roosting colony of monarch butterflies in Mexico is about 5 times 10 to the 6th grams. we want to write this number in standard notation. So we start off with the number that's in front of the multiplication sign. That's just the number 5. Now there is no decimal place specifically written in this problem, but we know that there's always a decimal underneath or behind the last number if there aren't any decimal places specified. So I'm going to put a decimal after the 5. And now, because this is going to be a very large number, 6 is positive, so it's going to be a very large number, I want to make my ocean waves going to the right. That's going to give me a big number. So I'm going to make 6 ocean waves going to the right. And I'm going to fill in each of those ocean waves with a 0. Alright, and now my decimal is behind that last 0. So I just go ahead and write it again, including all of the zeros. Put in commas. We know that the abbreviation for grams is just going to be G. So the mass of one roosting colony of monarch butterflies in Mexico is about 5 million grams. Alright, so far we've gone through 2 examples of converting standard notation into scientific notation, and we've gone through 2 examples of converting scientific notation back into standard notation. Now what I want you guys to do, I want you to copy down numbers 5 and 6, and I want you to work through those 2 on your own. I will expect you to have those 2 problems completed when I check in your notes tomorrow on Tuesday. Now I'm not sure if example 6 is coming through very clearly or not. It's supposed to say convert 2.1 times 10 to the 5th to standard notation. Sometimes the formatting messes up a little bit on these, but just make sure that you've got numbers 5 and 6 completed for Tuesday. Be sure to write down any questions that you have, and we'll go over those when you finish your notes and when we're back together in class on Tuesday.